Welcome to the peaceful space of sleep-friendly science, where tonight we will build a gentle thread to the stars, exploring the elegant and audacious dream of the space elevator. Tonight our story is one of quiet ambition, a dream of reaching for the heavens not with fire and fury, but with a silent, steady climb. It is a structure of almost impossible grace. Let your mind become still, and imagine a single shimmering thread connecting our world to the stars. Now settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1: The Tyranny of the Rocket. Feel the gentle but insistent pull of the earth beneath you. It is a constant, a fundamental truth of your existence. It is the invisible tether that holds you, the atmosphere, the oceans, and every living thing to the surface of this spinning world. Gravity is not a loud or violent force. It is a force of immense, unyielding patience. It has an unbreakable grip, and for all of human history, to even dream of leaving this world has meant finding a way to fight this grip. Our planet, in its beauty, sits at the bottom of a deep and powerful gravity well. Imagine it as a vast, invisible valley. We are born at the bottom of this valley, and to climb its steep, invisible slopes requires a colossal amount of energy. To escape the valley entirely, to reach the flat, open plains of interplanetary space, is the greatest physical challenge our species has ever undertaken. And for all of our history, from the first whispered dreams of space travel to the magnificent voyages of our current age, we have known only one way to make this climb. We fight. We use brute force. We build a tower of fuel and fire, point it at the sky, and try to outrun the dragon of gravity. We build a rocket. Let us contemplate the nature of a rocket launch. It is not a gentle or an elegant thing. It is a sustained, controlled explosion. It is a continuous act of violence, directed downwards with such ferocious power that it lifts a fragile vessel of metal and life upwards, against gravity's patient pull. A rocket launch is a deep guttural roar, a noise that is not just heard with the ears but felt in the very bones, a sound that tears at the very fabric of the air. It is a vessel strapped to the back of a barely tamed dragon, hoping the dragon flies in the right direction. And for all its sound and fury, for all its terrifying beauty, this method is profoundly, almost heartbreakingly inefficient. The rocket is its own worst enemy. Its greatest challenge is its own weight. To lift its precious cargo, a satellite, a telescope, a human crew, it must first lift itself. And most of itself is not cargo, it is fuel. And so, it must carry the immense weight of the fuel required to lift the fuel that is yet to be burned, which in turn is lifting the fuel that will be burned after that. It is like a mountain climber who must begin their journey by carrying a second mountain on their back, just to have the energy to carry a slightly smaller mountain for the next leg of the journey. For every 100 pounds of a rocket sitting on the launch pad, only a few precious pounds are the actual destination, the satellite or the capsule. The rest is the machinery and, overwhelmingly, the propellant. It is all discarded, burned up and cast away in a few furious minutes, just to give that tiny fraction of the original mass a final desperate push over the edge of the gravity well. This is the tyranny of the rocket equation. It is a brutal and unforgiving piece of mathematics that has dictated the terms of our relationship with space for a century. It is wasteful. It is dangerous. And in a way it feels like a relic of our infancy as a spacefaring people. It is like shouting to get someone's attention from across a quiet room. It works, but it is graceless. It lacks the quiet confidence of a more mature technology. So as you lie here, surrounded by the quiet of your room, let the thunderous roar of the rocket fade from your mind. And in the silence that remains, let us ask a simple, audacious question. What if we didn't have to fight? What if there was another way? A way that was not about overpowering gravity but about gently neutralizing it? A way that was not a shout, but a steady, silent, and graceful ascent? A way that required not a tower of fire, but a single shimmering thread. Section 2. A thread to the heavens. From the fading roar of the rocket, let a new idea rise in the quiet of your mind. An idea of such profound elegance and simplicity that it feels more like a dream, or a piece of ancient myth, than a feat of engineering. This is the idea of the space elevator. It is not a tower built from the ground up, a colossal structure of steel and concrete straining against its own weight. The space elevator is something far more graceful. It is not built up, it is lowered down. Imagine a thread, woven from a material of impossible strength, unspooled from a satellite in the heavens, its gossamer tip gently descending through the stratosphere, through the high, thin clouds, through the welcoming blue of the sky, until it finally touches the earth, anchoring our world to the cosmos above. This is a dream that has haunted the minds of scientists and storytellers for over a century. A Russian visionary named Konstantin Tsiolkovsky first imagined a celestial tower in 1895, inspired by the newly built Eiffel Tower. But it was the great science fiction writer Arthur C. Clarke who, in his novel The Fountains of Paradise, gave us the modern, more elegant vision. Not a rigid tower but a taut, shimmering ribbon. A tether. A bridge to the stars. Let us contemplate the nature of this structure. We must call it a cable or a ribbon or a tether, but these words feel too mundane, too industrial. Let us imagine it as it would appear in the sky. A single shimmering strand, so thin as to be nearly invisible, catching the light of the sun like a spider's silk spun between worlds. In the day it would be a faint silver line against the blue. At dawn and dusk it would blaze with the light of the sun, a vertical man-made sunset, a fiery pillar connecting the ground to a single unmoving star in the heavens. This is not a passive structure like a bridge or a road. It is an active one, a vertical railway. Along this unbreakable thread, electric vehicles, which we call climbers or lifters, would ascend and descend in a slow, steady, silent procession. Imagine a cabin like that of a high-speed train but climbing vertically. There is no roar of engines, no violent shaking, no crushing G-forces. There is only the quiet, efficient hum of electric motors, powered by lasers from the ground, gripping the ribbon and pulling the cabin upwards, into the sky. Your journey would begin at sea level, in the warm, humid air of the tropics. The climber would begin its ascent, and you would watch through a great window as the world gently receded below. You would rise through the clouds, those soft white continents of the sky, and emerge into the brilliant, unfiltered sunlight above. The blue of the atmosphere would deepen, from a soft powder blue to a rich, royal sapphire, and then slowly, majestically, it would fade to the perfect velvet black of space. The gentle curve of the earth would become apparent, a vast blue and white marble hanging in the void. Stars no longer twinkling would appear, hard, brilliant points of diamond light, not just above you but all around you. The journey would not take 8 frantic minutes like a rocket launch. It would take days. It would be a cruise, a scenic voyage through the layers of the sky. It would transform space travel from a rare, violent, and punishing ordeal into a routine, gentle, and accessible commute. The space elevator is not just a structure. It is a doorway. It is a highway that would open up the solar system, making the cost of lifting cargo and people into orbit a tiny fraction of what it is today. It is the dream of turning the empty space above our heads into a true extension of our world. It sounds like a fairy tale, a beanstalk from a children's story. It seems to defy the very laws of gravity and strength that we know. How could such a slender thread support its own immense weight, let alone the weight of a climber? How could it stand taut and true against the pull of the earth? Feels like magic. But its magic is rooted in the deep and elegant physics of the cosmos itself. Section 3. The Celestial Balancing Act. The image of this shimmering thread to the heavens is one of almost impossible grace. But our intuition screams a simple, powerful objection. Why doesn't it just fall down? This structure would be over 100,000 kilometers long, a ribbon of unimaginable length. How can it stand against the patient, relentless, and unforgiving pull of Earth's gravity? A skyscraper strains to support the weight of a few hundred meters. How can this gossamer thread support the weight of 100,000 kilometers? The secret is that the space elevator does not stand up by fighting gravity. It does not defy gravity. It achieves something far more elegant. It achieves a perfect balance with it. It is not a tower at all. It is a cosmic tug-of-war, where both sides are perfectly matched. Let us first feel the force pulling down. This is gravity. It is the Earth's desire to pull every single atom of the ribbon back towards its center. The closer an atom is to the Earth, the stronger this pull. So the bottom of the ribbon is being pulled down with the greatest force, and this force gradually weakens as you ascend. Now we need an opposing force, a force that pulls upwards. And for this we must look to the heavens. Imagine you are holding a weight on the end of a string and spinning it around your head. You feel a constant outward pull. The faster you spin it, the stronger the weight wants to fly away. This outward flinging tendency is the essence of orbital motion. It is the joyful outward fling that keeps the moon from falling into the Earth, and the Earth from falling into the sun. The space elevator is the string, and the Earth's rotation provides the spin. Now we must find the perfect place to put the weight, a place where the forces are in perfect harmony. There is a magical altitude in the sky, a very specific and sacred orbit, about 35,786 kilometers directly above the Earth's equator. This is the geostationary orbit. It is a celestial sweet spot. At this precise altitude, the speed required to orbit the Earth perfectly matches the speed of the Earth's own rotation. A satellite placed here will complete one orbit in exactly 24 hours. From the ground, it does not appear to move. It hangs motionless in the sky, a fixed and constant star. It is in a state of perfect equilibrium, where the downward pull of gravity is perfectly, exquisitely balanced by the outward fling of its orbital motion. This is the fulcrum of our space elevator. This is the balance point. Imagine the elevator as a colossal vertical seesaw, with its pivot point resting at this geostationary altitude. Now the piece of the ribbon that hangs below this point, the part stretching down to the Earth, is moving too slowly for its altitude. Gravity is winning the tug-of-war for this section. It wants to fall. It is the weight on one side of our cosmic seesaw. So to keep the entire structure taut, we must extend the ribbon far out into space beyond the geostationary point. And on the far end of this upper section, we must place a massive object. A counterweight. This could be a purpose-built space station, or perhaps a captured asteroid, a small mountain moved into place. This upper section of the ribbon, and the counterweight at its end, is now moving faster than is required for its orbit. For this section, the outward fling is winning the tug-of-war. It wants to fly away into space. This is the weight on the other side of our seesaw. And here is the beautiful celestial balancing act. The entire structure is designed so that the total upward pull from the outer section is slightly greater than the total downward pull from the inner section. The center of mass of the entire system, the ribbon, the climber, the counterweight, is carefully positioned at the geostationary point. The constant desire of the counterweight to fly away into deep space is what pulls the entire ribbon taut, keeping it stretched and straight all the way down to the surface of the Earth. It is not standing. It is flying. It is in a constant state of dynamic tension, a cosmic tug-of-war played between the Earth's gravity and the momentum of the heavens. It is a structure held in place not by the brute strength of compression, but by the elegant, perfectly balanced physics of the dance between worlds. The question is no longer how it stands up. The new question is, what on earth or off it could we possibly make it from? Section 4. Weaving an unbreakable thread. The celestial balancing act is a concept of breathtaking elegance. A cosmic tug-of-war, played out between gravity and orbital motion, holding a 100,000-kilometer ribbon perfectly taut. The physics works. The vision is sound. But as we descend from the pure, abstract realm of physics to the messy, practical world of engineering, we encounter the great, central dragon of this story. we come face to face with the problem of the material itself. What earthly substance could we possibly use to weave this unbreakable thread? Let us feel the forces at play. This ribbon must support not only the weight of the climbing vehicles, but its own immense weight. 100,000 kilometers of cable, hanging in a gravity field, generates a stress that is almost beyond comprehension. The point of maximum stress is not at the bottom, nor at the top, but at the geostationary point, the fulcrum where the weight of the lower section is pulling down with its full might. Let us try to build our ribbon from a familiar, strong material. Steel. The strongest steel alloys known to humanity are masterpieces of metallurgy, capable of withstanding immense forces. But if you were to try and build a simple steel cable, hanging it from geostationary orbit, it would be able to support only a few hundred kilometers of its own weight before snapping under the strain. Steel is far too heavy and far too weak for this celestial task. Materials like Kevlar or other advanced composites fare better, but they too fail the test. The simple, brutal truth is this: no conventional material that we can manufacture today is remotely strong enough to build a space elevator. For decades, this single insurmountable problem has relegated the space elevator to the realm of science fiction. It was a beautiful dream, but one for which we simply did not have the right thread. The dream was waiting for a miracle material. And then, in 1991, that miracle arrived. It was not forged in a great industrial furnace. It was discovered in the fine black soot of a carbon arc experiment. A Japanese scientist named Sumio Iijima, peering into this soot with an electron microscope, found something new. Tiny, perfect, and impossibly elegant structures. They were hollow tubes, their walls made from a single one-atom-thick sheet of carbon atoms, arranged in a perfect hexagonal lattice, like a rolled-up sheet of chicken wire. These were carbon nanotubes. Let us contemplate the nature of this material. It is a form of carbon, the same element that makes up the soft graphite in your pencil and the hard, brilliant diamond on a ring. But in this new tubular form, carbon displays a strength that is almost mythical. A single carbon nanotube is only a few nanometers wide, thousands of times thinner than a human hair. But atom for atom, it is the strongest material ever discovered. A thread woven from these nanotubes would be, in theory, 100 times stronger than steel, at only a fraction of the weight. This is the gift of the carbon bond, the most versatile and powerful bond in chemistry. In a nanotube, each carbon atom is bonded to 3 of its neighbors in a perfect, stable, and repeating pattern. There are no weak points, no grain boundaries, no microscopic cracks where a failure can begin. The forces are distributed perfectly across the entire structure. The strength of the material is the strength of the chemical bond itself. This was the miracle the dream had been waiting for. Here, finally, was a material with a high enough specific strength, a measure of its strength-to-weight ratio to make the celestial thread a physical possibility. A ribbon woven from carbon nanotubes would be light enough and strong enough to support its own immense weight, and still have plenty of strength left over to carry the climbers. The dragon of the material problem had, in theory, been slain. But a theoretical possibility is not an engineering reality. The great challenge we now face is not one of discovery, but one of manufacturing. We can currently grow perfect individual carbon nanotubes that are a few centimeters long in our laboratories. But the space elevator requires a ribbon 100,000 kilometers long. It is like knowing how to forge a single perfect link of a chain, but not yet knowing how to produce the millions of links needed to build an anchor chain for a great ship. Scientists and engineers around the world are now tackling this grand challenge. They are exploring ways to spin long, continuous fibers from a forest of nanotubes, like spinning silk from a cocoon. They are experimenting with other miraculous, two-dimensional materials, like graphene and boron nitride, which also possess this mythical strength. The journey from the laboratory bench to a celestial scale ribbon is still a long and difficult one. But for the first time in human history, it is no longer a question of finding a magical substance. We have found it. The question now is one of craft. It is the patient, difficult and profoundly human task of learning how to weave our unbreakable thread to the heavens. Section 5. The anchor in the sea. The vision is taking shape. The physics of the celestial balance is sound. The miracle material, the carbon nanotube, has been discovered, its theoretical strength sufficient for the immense task. We now have our unbreakable thread. But a thread, however strong, must be anchored. It cannot simply touch the earth. It must be tethered to it firmly and securely. This brings our grand cosmic vision down to a very real and practical place. We must now design the foundation of our beanstalk. We must build the earthport. Where on our vast spinning globe would we place this gateway to the stars? The physics of our balancing act gives us a clear and non-negotiable answer. The anchor must be located on the equator. The entire structure of the elevator is built upon the principle of geostationary orbit, which exists only as a perfect ring directly above the Earth's equator. The ribbon must hang straight down from this point, like a plumb line from the heavens, and so its base must lie on the imaginary line that separates the northern and southern hemispheres. This geographical constraint narrows our search, but it still leaves us with vast stretches of ocean and land. The next great consideration is one of safety and stability. The elevator ribbon, for all its strength, would be vulnerable. And its greatest terrestrial threats are the wind and the weather. A hurricane, a typhoon, a tornado. These great, churning engines of atmospheric violence would exert a terrifying force on the lower section of the ribbon. And lightning, the raw electrical power of a thunderstorm, poses another immense danger. We need to find the calmest, most peaceful place on Earth. And so, our search moves away from the land and out onto the open ocean. The equatorial regions of the Pacific Ocean are home to a region of serene and predictable calm, known as the doldrums. Here, the great weather systems of the northern and southern hemispheres meet and cancel each other out. It is a place of light winds and tranquil seas, a region largely free from the violent storms that plague other parts of the globe. Here, in this ocean sanctuary, is the perfect place to build our anchor. But you cannot build a fixed foundation on the shifting floor of the deep ocean. The anchor must be mobile. It must be a colossal floating platform, a man-made island of steel and concrete, a structure larger and more massive than any vessel ever built. Imagine a platform several kilometers across, a floating city dedicated to a single purpose, to be the root of our connection to space. This is the Earthport. It would be a place of quiet, humming activity. At its center would be the anchor point itself, the terminus, a complex and heavily engineered structure where the shimmering nanotube ribbon is securely fastened to the Earth. The ribbon would not be rigid here. It would be connected to a system of immense, computer-controlled winches and shock absorbers, allowing the platform to move gently with the ocean currents and swells, preventing any sudden, snapping forces from being transmitted up the delicate thread. Surrounding this central anchor would be the infrastructure of a spaceport. There would be great hangars where the climbers are prepared and loaded with their cargo. There would be control centers filled with technicians, monitoring every aspect of the elevator's health, from the strain on the ribbon to the weather patterns 1,000 miles away. There would be habitats for the thousands of people who would live and work on this floating city. And most importantly, there would be power plants, perhaps drawing clean energy from the temperature difference of the deep ocean water, generating the immense electrical power needed to drive the lasers that will push the climbers on their journey to the stars. The platform would not be entirely alone. It would have the ability to move slowly under its own power. If a large storm were to deviate from its usual path, or if a piece of orbiting space debris were predicted to come too close to the ribbon, the entire floating city could gently maneuver itself out of harm's way, dragging the base of the colossal ribbon with it. It is a paradox of scale, a structure of immense size and stability, yet with the gentle grace of mobility. This floating, equatorial island is the crucial, first step. It is the earthly root from which our celestial tree will grow. It is the quiet, humming harbor from which the silent ships will depart on their slow, steady voyage to the shores of other worlds. It is the place where our journey to the stars truly begins. Section 6. The Long Quiet Ascent. The anchor is set in the calm, equatorial sea. The unbreakable thread shimmers in the tropical sunlight, a line of pure potential rising to a fixed point in the heavens. The climber, a cabin of polished metal and wide, crystal-clear windows, waits for you in the bustling harbor of the Earthport. The doors close with a soft, reassuring hiss. There is no countdown, no frantic final check, no roar of engines. There is only a gentle, forward motion as the climber glides towards the base of the ribbon and, with a series of quiet metallic clicks, securely attaches itself. The journey begins not with a bang, but with a hum. Let us embark now on this long, quiet ascent. Feel a gentle, persistent acceleration as the electric motors engage, their powerful magnetic wheels gripping the carbon nanotube ribbon and pulling you upwards. The initial climb is slow, a walking pace, as you clear the massive structures of the Earthport. The great floating city shrinks below you, becoming a neat geometric pattern on the surface of the deep blue water. As you gain altitude, the climber accelerates to the speed of a high-speed train, a few hundred kilometers per hour. The ascent is smooth, silent, and unwavering. The only sound is the soft hum of the life support systems and the whisper of the recycled air. The world outside your window begins to transform. The great white puffy castles of the troposphere, the clouds you are used to seeing from above in an airplane, are now below you. You climb through them, into the serene deep blue of the stratosphere. Hours turn into a day. You have now climbed 100 kilometers, past the invisible line where the atmosphere is considered to have ended and space has begun. The blue of the sky has deepened to a profound, dark indigo, and the first brightest stars have begun to appear, no longer twinkling, but shining with a steady, hard light. The gentle curve of the earth is now undeniable, a vast sweeping arc of blue and white against the perfect black. You continue to climb. For days, you pass through the orbits of the lowest satellites, the International Space Station gliding silently past. Far below you, a brilliant man-made star completing its own much faster journey around the world. You traverse the Van Allen belts, the great, invisible rings of radiation that surround our planet, the climbers shielding quietly protecting you from their energetic particles. The Earth continues to shrink, no longer a landscape but a planet, a beautiful swirling marble of blue, white, and green, hanging in the infinite velvet darkness. The full moon, when it appears, is no longer a distant flat disk, but a stunning three-dimensional sphere, a sister world of gray and silver. You are now approaching the fulcrum of your journey. After several days of steady climbing, you arrive at the geostationary point, 35,786 kilometers above the world of your birth. Here you might pause. A great bustling space station would likely be built at this altitude, a midway point where climbers dock and passengers and cargo can be transferred. This is the great crossroads of the sky. From here, other ribbons might stretch out, connecting to different points on the Earth's equator. This is the central hub of the new interplanetary transport system. Looking down from this incredible vantage point, the Earth would appear as a vast, beautiful disk, filling a huge portion of your view, its continents and weather patterns laid out before you like a living map. And it would hang motionless in the same spot in the sky always. You are now perfectly matched to its rotation. But your journey is not over. The ribbon continues to stretch upwards, and so your ascent resumes. Now as you climb, a strange and wonderful new sensation begins. The relentless pull of gravity, which has been slowly weakening your entire journey, is now being overcome by the outward, centrifugal fling of your motion. You begin to feel lighter. A gentle but persistent force is now pulling you upwards, away from the Earth. You are no longer climbing out of the valley. You are sliding up the outer slope of the cosmic seesaw. The Earth shrinks further, from a great disk to a bright blue star. You are now truly in the high country of the solar system, ascending towards the great silent counterweight that is the anchor of this entire impossible structure, the port to the worlds beyond. Your long, quiet ascent has transformed you. You left as a creature of the earth. You are arriving as a citizen of the solar system. Section 7. A ladder of light. You are gliding upwards, a silent passenger on a thread to the stars. The quiet, persistent hum of the climber is your only companion, a sound of immense but gentle power. And in this serene ascent, a fundamental and practical question arises in the quiet of your mind. Where does this power come from? A journey of 100,000 kilometers, lasting for days on end, requires a colossal amount of energy. What is the fuel for this celestial voyage? The climber carries no great plume of fire, no vast and heavy tanks of propellant. What is the source of its silent, steady strength? The problem of power is, in its own way, as profound as the problem of the material. And once again, the elegant solution lies in not fighting a problem, but in gracefully sidestepping it. The first temptation might be to load the climber with its own power source, to equip it with immense, powerful batteries, for instance. But here we encounter the old ghost of the rocket equation, the tyranny of mass. The batteries required for such a long journey would be incredibly heavy. And to lift that heavy battery you would need more power, which would require an even heavier battery, which would require even more power. It is a vicious cycle that quickly becomes impossibly inefficient. What about solar panels, to drink the free and abundant light of the sun? This is a beautiful idea, and for a part of its journey, the climber will indeed be bathed in brilliant, unfiltered sunlight. Solar panels would certainly be a part of the system, perhaps powering the life support and the internal systems of the cabin. But this cannot be the primary source of motive power. For long stretches of its journey, the climber would be in the deep shadow of the earth, plunged into a darkness where its solar panels would be useless. And to generate enough power, the panels would need to be vast, turning our sleek, elegant climber into a clumsy, fragile kite, susceptible to the thin but persistent atmospheric drag in the lower parts of its climb. The true solution, like the elevator itself, is one of radical elegance. It is a solution that says, what if the climber didn't have to carry its power at all? What if the power was delivered to it moment by moment on its journey? What if we could build a ladder of pure light? Let us return our gaze to the great, floating earthport in the calm equatorial sea. At its heart, or perhaps on several dedicated platforms surrounding it, would be a new kind of engine. A phased array of immensely powerful ground-based lasers. These are not weapons. They are fountains of light. Their purpose is to generate a steady, focused, and powerful beam of photons, a river of pure energy, aimed with breathtaking precision at the ascending climber. Now look at the climber itself. On its underside, facing down towards the earth, is not a rocket nozzle, but a vast, dark, and beautiful photovoltaic panel, a sun catcher. But this is no ordinary solar panel. It is a work of art, a surface specifically and perfectly tuned to be receptive to one single frequency of light, the exact frequency of the laser beam from the ground. While a normal solar panel might convert 20 or 30% of the sun's broad-spectrum light into electricity, this specialized receiver could be vastly more efficient, perhaps converting over half of the laser's pure, monochromatic light directly into motive power. And so the climber ascends its ladder of light. The laser beam is the invisible rail, the umbilical cord of energy connecting the traveler to its mother world. The climber simply drinks the light, converting the stream of photons from below into the quiet, electrical hum that drives its motors. The heavy, complex, and powerful energy generation system is left safely on the ground. The climber itself can be designed to be as light, as simple, and as elegant as possible. It is a system of profound grace. But what of the challenges? What happens when a cloud passes over the earthport, obscuring the laser's view? The atmosphere itself, with its shimmering turbulence, would cause the beam to waver and lose its focus. The solution lies in cooperation and intelligence. There would not be one laser station, but a network of them, scattered along the equator around the globe. As the Earth turns or as weather obscures one station, the task of powering the climber would be passed seamlessly to another station, thousands of miles away, in a celestial digital handshake. And the lasers would be equipped with adaptive optics, the same technology used in our greatest telescopes. A flexible mirror, adjusting its shape thousands of times a second, would predistort the laser beam, canceling out the twinkling of the atmosphere and ensuring a steady, focus point of light arrives at the climber, 100,000 kilometers away. This is the quiet, humming heart of the elevator's motion. It is not brute force. It is a silent transfer of power across an immense distance, a conversation written in photons, a ladder of light upon which we can, one day, gently and peacefully, climb to the stars. Section 8. Dangers in the Void. Our journey has been one of serene beauty, a quiet ascent on a ladder of pure light. The physics is sound, the material is imagined, the power source is elegant. In the clean, perfect world of our imagination, the space elevator is a flawless bridge to the cosmos. But the universe is not a clean or a perfect place. And between the dream and the reality lies a host of immense and formidable challenges. The elevator must exist not in a perfect vacuum of thought, but in the real and often dangerous void of space. Let us now, with a calm and steady mind, contemplate the dragons that lie in wait along this celestial path. The first and perhaps most persistent of these dangers is a threat of our own making. The space around our planet is not empty. It is a junkyard. For 60 years we have been throwing things into orbit, and much of it has stayed there. The sky is filled with a swarm of space debris, a cloud of millions of tiny man-made meteoroids. There are dead satellites, discarded rocket stages, frozen flecks of paint, and fragments from past collisions. And they are all moving at breathtaking orbital velocities, tens of thousands of kilometers per hour. A fleck of paint traveling at these speeds has the kinetic energy of a bowling ball. A lost wrench has the impact force of a stick of dynamite. Our slender stationary ribbon, 100,000 kilometers long, would present a vast and unavoidable target for this cloud of tiny hypervelocity bullets. A single direct impact from a piece of debris of any significant size could sever the ribbon, a catastrophic failure that would send the entire structure whipping back into space and wrapping around the Earth. The solution to this danger must be one of constant, vigilant awareness. The elevator would require its own dedicated, ground-based radar and optical tracking systems, a celestial air traffic control, mapping the position and trajectory of every known piece of debris. The ribbon itself would not be a single solid strand, but a woven mesh-like structure, so that the very smallest particles could pass harmlessly through its gaps. And for the larger, more dangerous threats, the elevator must have a way to dodge. The anchor platform at sea could gently move the base of the ribbon, and perhaps the ribbon itself could be made to ripple, to generate a slow, gentle wave that travels up its length, causing a section to move out of the path of an oncoming piece of debris. The elevator must be not just strong but nimble. The next great danger comes from the Earth itself. The ribbon passes through our own dynamic atmosphere. We have already considered the threat of storms at its base. But higher up there are other more subtle forces. The high-altitude jet streams would push on the ribbon, causing it to oscillate and flutter, like a guitar string plucked by an invisible hand. These vibrations, if left unchecked, could build up into a resonant wave that could threaten the stability of the entire structure. The elevator would need a system of active dampers, small robotic devices that would crawl up and down the ribbon, sensing these vibrations and gently pushing against them to cancel them out, like a finger gently touching a ringing string to silence it. And then there is the danger of the invisible. As the climber ascends, it passes through the Van Allen radiation belts, great, donut-shaped regions of high-energy particles trapped by the Earth's magnetic field. While a rocket passes through these belts in a matter of minutes, The elevator's journey would take hours or days. Passengers and sensitive cargo would require significant shielding to protect them from this constant, invisible rain of radiation. Even the sun becomes a threat. A powerful solar flare can send a wave of charged particles, a coronal mass ejection, washing over the Earth. This could induce powerful electrical currents in the long, conductive ribbon, potentially overwhelming its systems. The elevator would need to be able to electrically isolate itself to weather these solar storms as they pass. These are not small problems. They are immense engineering challenges, each one requiring new technologies, new levels of precision, and a new kind of long-term thinking. Building the space elevator is not like building a bridge. A bridge once built is largely static. The elevator would be a living, dynamic thing. It would be a 100,000-kilometer-long organism, constantly sensing its environment, constantly adjusting, constantly repairing itself. It is a challenge that requires us to be not just builders, but celestial gardeners, forever tending to this strange and beautiful new plant we have seeded in the heavens. Section 9. The port to the solar system. Your long, quiet ascent is nearing its end. The climber has carried you for days, past the silent geostationary crossroads, into the high country of the cosmos. The Earth is now a brilliant, distant blue-white star, the brightest jewel in a sky of infinite black. The gentle upward pull of the centrifugal force is now at its strongest, a constant and reassuring presence. And ahead, growing from a point of light into a vast and complex structure, is your destination. You are arriving at the top of the world. You are arriving at the counterweight. Let us banish the simple image of a dead rock on the end of a string. This is not a mere anchor. It is the purpose of the entire structure. It is the port, the harbor, the grand celestial dock from which the true voyages will begin. Imagine a structure of immense scale, perhaps a captured asteroid, hollowed out and transformed into a bustling city. Or a purpose-built space station, a great spinning wheel over a kilometer across, its rotation providing a gentle artificial gravity for its inhabitants. The climber glides towards it, its journey of over 100,000 kilometers complete. It approaches a docking bay, and with a series of quiet, precise maneuvers, it latches on with a final gentle sigh. The doors open and you step out, not into the weightlessness of space, but onto the solid floor of a grand concourse. Through vast, diamond-paned windows, you can see the shimmering ribbon you have just ascended, stretching down, 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 towards the distant sunlit speck of your birth world. This station is a hive of activity. It is a place of science, of industry, and of departure. Here, telescopes gaze out into the universe, free from the blurring distortion of Earth's atmosphere, seeing the cosmos with a clarity never before possible. Here, materials mined from the moon or the asteroids can be processed and assembled in the vacuum of space, building new ships and new structures. And here, in the great departure bays, the interplanetary vessels are being prepared. And this is the true magic of this place. This is why the elevator was built. From this high perch at the very top of Earth's gravity well, the tyranny of the rocket is a forgotten memory. Gravity is no longer an enemy to be fought. It has become a tool to be used. Imagine a ship, ready to depart for Mars. On Earth, this would require a colossal multi-stage rocket and a terrifying fiery ascent. Here at the counterweight, the departure is a thing of silent, graceful beauty. The ship is simply released from its docking clamp. No engines are fired. It is just let go. The counterweight is traveling at immense speed, whipping around the Earth at over 10,000 kilometers per hour. By releasing the ship at the right moment, as it moves in the same direction as Earth's rotation, you are giving it an immense slingshot assist. It is thrown outwards away from the Earth, its momentum carrying it into a higher, wider orbit, a perfect trajectory that will, after months of quiet coasting, intercept the orbit of Mars. You do not need to fight gravity. You simply use the momentum of the elevator itself to give you the initial push. The entire planet has become the engine. And what if your destination is one of the inner worlds, Venus or Mercury? The process is just as elegant. The ship is released from the counterweight, but this time, it is given a slight nudge in the direction opposite to the station's travel. This small, retrograde push causes it to lose a little of its orbital energy. And so it begins a long, slow, graceful fall towards the Sun, its new orbit carrying it inwards, to a rendezvous with the inner planets. This is the port to the solar system. It is a place where leaving Earth is no longer a monumental struggle, but a routine, efficient and gentle act of release. The cost and complexity of interplanetary travel would plummet. The planets would cease to be distant, abstract points of light, and would become true destinations, neighbors in our sun's city that we can now visit. Earth is no longer the sole outpost of humanity. It is the anchor of a bridge that has made the entire solar system our home. Section 10. Unfurling the first ribbon. We have dreamed a great dream together. A shimmering thread to the heavens, a celestial balancing act, an anchor in a tranquil sea, and a silent port at the top of the world. The vision is complete. It is beautiful. It is audacious. And it is, we believe, possible. But it leaves us with one final profound and beautifully practical puzzle. It is the ultimate chicken and the egg problem. How do you build the first one? You cannot use the elevator to build the elevator. So how is the first impossibly long ribbon ever put into place? The answer, ironically, begins with the very technology the elevator is designed to replace. It begins with the old way. It begins with the sound and fury of a rocket. Imagine a single, heavy-lift rocket, the largest and most powerful we can build, standing on a launch pad. Its mission is not to carry a satellite or a human crew into a low orbit. Its mission is to carry a single, precious, and very heavy spool of thread. On this spool, wound with the utmost care, is the seat of the elevator, the first thin, pilot ribbon of carbon nanotubes, 100,000 kilometers long, but perhaps no wider than a piece of dental floss. The rocket roars to life, a final necessary act of brute force, lifting this precious spool up through the atmosphere, past the edge of space, and placing it into a temporary orbit. Now, a second, more specialized spacecraft approaches the spool. This is the deployer, a celestial construction drone. It carefully grapples the spool and then, using its own highly efficient engines, it begins the slow, patient process of raising its orbit. It spirals outwards day by day, on a journey that will take months, climbing from low Earth orbit up to that magical, sacred altitude. The geostationary orbit, 35,786 kilometers high. Once it arrives, it parks itself. It is now perfectly stationary above a single point on the equator. The great deployment is about to begin. The deployer spacecraft takes the free end of the pilot ribbon from the spool, and then with the utmost delicacy, it begins to lower it. Imagine this moment. A single shimmering, nearly invisible thread of carbon, unspooling downwards, towards the distant blue marble of the Earth. This is a process of immense, slow and careful precision. As the ribbon descends, the deployer must use its thrusters to gently counteract the gravitational pull, keeping its own position perfectly stable. At the same time as the ribbon is descending towards the Earth, the great spool itself, the main body of the payload, is being propelled in the opposite direction, outwards into a higher orbit. It is being sent on its long journey to become the initial seed counterweight. This is the great simultaneous act of unspooling in both directions, a celestial act of unfurling. For weeks, the pilot ribbon descends. It passes through the high atmosphere, buffeted by winds, its path tracked with a precision that borders on the miraculous. On the floating Earthport in the ocean below, a fleet of high-altitude aircraft and specialized capture vehicles wait, their sensors trained on the sky, ready to catch this thread from heaven. And then, finally, the moment arrives. The end of the ribbon is captured, brought down, and secured to the great anchor at the heart of the floating city. A connection has been made. A single gossamer thin thread now links the earth to the heavens. It is far too fragile to carry a climber. But it is a guide. It is a scaffold. It is the beginning. Now the true work begins. The first generation of robotic climbers, small and light, are attached to this pilot ribbon. They are not carrying cargo or people. They are carrying more ribbon. They begin their slow, patient ascent, each one laying down a new strand of carbon nanotube alongside the first, weaving the ribbon thicker and stronger with every pass. Like spiders, they crawl up and down this first fragile thread, strengthening it, reinforcing it, turning the dental floss into a cord, the cord into a rope, the rope into a great, flat, shimmering ribbon, wide enough and strong enough to bear the weight of the dreams to come. This is not a fast process. It would take years of this patient robotic weaving. But with each new thread, the elevator grows stronger, its capacity increases, and the dream solidifies into a physical reality. It is a slow, organic process of creation, a barn raising on a cosmic scale. And it all begins with a single fragile thread, unfurled from the heavens, a quiet promise of the bridge that is to come. And so our grand construction project for the night is complete. The thread is woven, the anchor is set, and the silent port to the solar system awaits. May this vision of quiet, ambitious, and elegant engineering leave you with a sense of peaceful possibility. A sense that even our grandest dreams are not impossible, but are simply waiting for the right materials, the right idea, and the patient, steady work of creation. The universe is filled with such quiet possibilities. And tonight you can rest, knowing you are a part of a species that dares to dream them. Sleep well, and may your dreams be filled with silent, steady ascents. Good night.